Statistical methods date back at least to the 5th century BC. Statistics was originally called state arithmetic and has strong roots in real-world applications. For example, the Roman Empire reached its greatest expanse during the reign of Trajan, with a population of roughly 60 million people. In 117 AD, it stretched from Britain to Syria and from the north coast of Africa to the centre of Europe. That's an enormous number of people to collect, organise and interpret information about. Statistics has grown and developed since Roman times and has been influenced by the following areas. Biostatistics is a specialised field of statistics in general. There are two main branches of statistics. One is focused on describing and communicating information simply. The other on drawing conclusions from data and inferring them to different but often related situations. Information is collected by observing or measuring something. One observation is referred to as a datum, while a collection of observations or measurements are called data. Let's take a closer look at descriptive statistics. Both of these figures are examples of descriptive statistics. Each blue dot in figure 1 represents one of tens of thousands of confirmed cases of Lyme disease in 2011. Rather than examining CDC records for every county of every state in the US, these statistical maps summarise, organise and simplify the data into a form that's more easily communicated and understood. Think about the sheer volume of data summed up in these two figures. We can readily appreciate areas associated with high or low risk of contracting Lyme disease just by looking at them. Here are two further examples of descriptive statistics that summarise, organise and simplify tens of thousands of Lyme disease data. What information is being communicated here? Researchers usually study a sample, but they're really interested in answering a question about a specific group of individuals. In statistical terminology, the entire group that a researcher wishes to study is called a population. Populations can obviously vary in size, from extremely large to very small, depending on how the investigator defines the population. Populations don't even need to consist of people. It could be a population of rats, businesses, components manufactured in a factory, really anything an investigator wants to study. Populations are typically very large, and it's usually impossible for a researcher to examine every individual. It's also far too expensive and it would take too long. Instead, researchers select a smaller, more manageable group from the population and focus their studies on these individuals. This sample of people is intended to be representative of its population. Just as we saw with populations, samples can vary in size. There's likely to be hundreds or thousands of people in these samples. Or one study might examine a sample of only 18 people, let's say from New Haven. Samples should be representative and generalisable. Remember that the research started with a general question about the population. To answer the question, a researcher studies a representative sample and then generalises the results from the sample to the population. If we studied sample 1 here, could whatever we learn be applied to the larger population of New Haven? What if we use sample 2 instead? Or how about sample 3? Same question. If we studied this sample, could whatever we learned be applied back to New Haven? If we had to choose one of the three, sample 3 is the most representative in terms of sex and race. A characteristic that describes a population, usually a numerical value, is referred to as a parameter, while a characteristic that describes a sample is called a statistic. Here are some examples of both. Typically, Every population parameter has a corresponding sample statistic, and a substantial amount of biostats is concerned with the relationship between sample statistics and the corresponding population parameters. For the purposes of statistical notation, Greek letters such as mu or sigma are used to indicate parameters, while Roman letters, like the ones we use in the English alphabet, indicate statistics. Now let's take a closer look at inferential statistics. As I said earlier, inferential statistics consist of techniques that allow us to study samples and then make generalizations about the populations from which they were selected. Sticking with 1st century Romans, let's say we wanted to measure how long a typical Roman citizen lives. Rather than determining that for millions and millions of people, we could select and observe a smaller, more manageable sample of 60 individuals, then calculate their average life expectancy. The average of 25 years we calculated from the sample of 60 forms our estimate for the whole Roman population. We're inferring from our sample data that the life expectancy at birth of a Roman citizen is 25 years. However, if the actual life expectancy is 28 years, there would be a discrepancy of 3 years between the true population parameter and the sample statistic. We call this discrepancy sampling error. If we wanted a better, more accurate estimate, we could select a larger sample of 120 individuals and calculate their average life expectancy. This time around we get a discrepancy, or sampling error, of 1 year between the true population parameter and the sample statistic. We don't expect the statistics from a sample to be perfect. There always will be some margin of error when sample statistics are used to represent population parameters. So sampling error is normal and can be minimized by using sufficiently large and randomly selected samples. Researchers are typically interested in specific characteristics of the individuals in the population or sample, or they're interested in outside factors that may influence the individuals. Something that can change or have different values is called a variable. Constants are characteristics that are fixed for each individual and cannot change. There are a handful of different types of variables that we consider in research. Two necessary for good research are independent variables and dependent variables. The variable that is manipulated by the experimenter is called the independent variable. The dependent variable is the one that is observed to assess the effect of the independent variable. To help you identify which is which, here are some quick tips. The independent variable is the thing that is being controlled, or decided, or manipulated, or assigned by the researcher. The dependent variable is what's being measured. The manipulation of the independent variable usually comes before the measurement of the dependent variable, so looking at what comes before is another way to help you find which is which. Let's talk through an example. A researcher examines the effects of two variables in memory. One variable is beverage, let's say coffee or water, and the other variable is the aspects of a story to be remembered. Drinking the beverage comes before the study participants listen to the story and then try to recall its aspects. The researcher decides who gets a coffee and who gets water. So the beverage is the independent variable. That's the thing that the researcher is manipulating. It also comes first. The aspects of the story, that's the dependent variable. That's what's being measured to help us assess the effects of beverage on memory. Two other types of variables are between subjects and within subjects variables. Between subjects variables change from person to person to person. For example, I have B negative blood. My brother has B positive. I'm 6 years older than he is. So age and blood type differ between us. They're between subjects variables. Within subjects variables are characteristics of one person that change over time. For example, my heart rate is different when I'm sleeping than when I'm exercising, or the number of vaccinations I've had will change over the course of my life. So measuring a characteristic of an individual at different time points, that's a within subjects variable. The names for these variables are fairly descriptive. Some research studies are conducted simply to describe individual variables as they exist naturally. But most research is intended to examine the relationship between variables. 3 important types of study to help us do this are correlational studies, experimental studies, and quasi-experimental studies. In the correlational method, 2 different variables as they exist naturally are observed to determine whether there is a relationship between them. The results from a correlational study can demonstrate the existence of a relationship between 2 variables, but they do not provide an explanation for the relationship. For example, supervisors' sense of humour and people's job satisfaction. Is the funny boss the cause of the job satisfaction? Maybe, maybe not. There are many possible explanations for the relationship, and we don't know exactly what factor or factors are responsible here. Maybe it's the work environment. Maybe it's very relaxed and comfortable. That work environment is the cause of the sense of humour and the cause of the job satisfaction. How about the number of DVRs in a household and a student's SAT scores? Does owning more DVRs cause you to have a better score? Or is something else, a third factor, something related to the other 2, is that the cause? A family that's well balanced, functional, and that has a high socio-economic status is probably going to have more DVRs and provide more resources for the educational needs of their children than families who struggle financially or who are dysfunctional. Correlational studies can only tell us a relationship exists between 2 variables. They cannot in any way demonstrate cause and effect. To demonstrate a cause and effect relationship between 2 variables, researchers must use the experimental method. That's its goal. An experiment attempts to show that changing the value of one variable will cause changes to occur in the second variable. For example, is there a cause and effect relationship between administering the polio vaccine and the number of people in the population who have polio? In other words, does giving the vaccine cause a decrease in the incidence of polio? To accomplish the goal of demonstrating cause and effect, the researcher must use manipulation and control. The researcher has to manipulate the giving of the vaccine, giving it to some people and not to others, or increasing the number of people it's given to. They will then measure the number of polio cases in the population or sample. The researcher must also exercise control over the research situation to ensure that other unrelated variables do not influence the relationship being examined. We call these confounding variables. Confounding variables are the enemy of good research. In this case, age and nutritional status of participants in the experiment may be confounding variables. Very young and very old people are more susceptible to disease. Likewise, people who are underfed or malnourished. An observed difference in polio incidence may be due to variation in these characteristics rather than the vaccinations. Whenever a research study allows more than one explanation for the results, the study is said to be confounded because it's impossible to reach an unambiguous conclusion. In informal conversation, there's a tendency for people to use the term experiment to refer to any kind of research study. You should realise, however, that the term only applies to studies that satisfy the specific requirements outlined earlier. As a result, there are a number of other research designs that are not true experiments but still examine the relationship between variables. One of these is the quasi-experimental method. This is a non-experimental study because it lacks the rigorous control needed. This type of study compares pre-existing groups, so the researcher cannot control the assignment of participants to the groups or ensure equivalent groups. If you're studying the relationship between sex and seasonal affective disorder, You can't randomly assign half of your participants to be male and half to be female. You could separate them into male and female groups based on their pre-existing sex, but you cannot manipulate that between subjects variable. In other words, the researcher cannot manipulate their genetic sex and then measure how well they do in terms of depression during the winter months. In the second example, it would be unethical to manipulate and assign people to two different groups that receive their medication via the old or via the new system, and then step back to observe the number of medication-related adverse events that result. Ethics restrict our level of control here, and mean that this study is also considered non-experimental. Let's go through some examples to practice identifying the type of study involved. Example 1. An occupational therapist is interested in the relationship between dog owners and number of household falls among older people. A total of 530 subjects with an average age of 77 years are recruited primarily before discharge from selected hospital wards. The OT records those who have pet dogs and observes the number of falls, ascertained over a 12-month follow-up period using a monthly falls calendar. What kind of study is this? The things to consider are the number of variables measured or manipulated and the degree of control. This chart can help you. In example 1, the OT is recording, or in other words measuring, two variables. Those subjects who have dogs and the number of household falls. There is no manipulation or control. The OT is not giving dogs to some people and taking them away from others. This is a correlational study. Example 2. A researcher is testing the effect of alcohol in memory performance. He gives one group of subjects a bottle of vodka and another a non-alcoholic substance that tastes like vodka. Each group then learns a list of words and attempts to recall them. The number of words correctly recalled for each group is recorded. What kind of study is this? The researcher manipulates one variable, the beverage. One group of people are assigned vodka to drink, and the other group are assigned a non-alcoholic fake vodka. Then after this manipulation, the researcher measures one variable, the number of words recalled from a list. This is an experimental study. Example 3. A social psychologist is interested in sex differences in math performance. She randomly selects men and women from New Haven and has them solve a series of equations. The number of equations correctly solved for each participant is recorded. What kind of study is this? The psychologist is measuring one variable, the number of equations solved correctly. She can't manipulate the pre-existing sex of the subjects. This is a quasi-experimental study. Example 4. A clinical psychologist is interested in the effectiveness of a new antidepressant drug. He collects scaled depression scores from a group of individuals diagnosed with depression at time 1. All individuals then take the drug and are measured again a month later at time 2. What kind of study is this? The psychologist manipulates one variable, the antidepressant drug. It's being controlled and assigned. In this case, to all the participants. One variable is being measured, the depression scores. This one variable is being measured twice, before they take the drug and then 1 month later. This is an experimental study. It's important to know the types of variables you're dealing with in order to choose the correct statistical techniques to analyze your data. The variables researchers measure can also be characterized by the types of values that can be assigned to them. Researchers use both discrete and continuous numerical observations to quantify variables. Discrete observations can only take on whole numbers, not values in between, so no values with fractions or decimals. For example, in terms of British politics, you can be a member of the Liberal Democrats, or the Scottish National Party, or the Conservative Party, but you can't be 3/15 of one and 12/15 of another. Similarly, individuals have whole numbers of vaccinations, not 3.43 vaccinations of tetanus and 0.74 vaccinations of hepatitis B. On the other hand, continuous variables can take on a full range of values. Numbers out to several decimal places are fine. In other words, an infinite number of potential values exists. For example, one person might complete a task in 12.839 seconds. Someone else might complete it in 14.870 seconds. The possible values are continuous, limited only by the number of decimal places we choose to use. Let's take a closer look at continuous and discrete variables. It's rare for continuous variables to be identical for two different individuals. Each measurement category is really an interval defined by boundaries. If we measure blood pressure to 4 decimal places, we'll observe that every person is different from the next. Those values to 4 decimal places fall on a continuous line that can be divided into specific categories defined by boundaries. 118, 119, 120, 121, and so on. Let's look at this concept in another way, in terms of physical location in Connecticut. We can be present in many different physical locations in Connecticut, and yet still be authentically in Connecticut. Physical location within Connecticut is a continuous variable. One person can be in North Haven, one in Mystic, another in Danbury, yet all three are genuinely within Connecticut. Connecticut is adjacent to Massachusetts. They share a border. Both states are actually intervals within New England that are defined by boundaries. Although physical location is continuous, the category location we call Connecticut is a fixed interval defined by the New York, Massachusetts, and Rhode Island borders. Or another way of explaining this, the I-95 can be thought of as a continuous highway running between Florida and Maine. Physical location on I-95 is also a continuous variable. And state borders divide the I-95 into discrete sections. When driving from North Haven to New York City, you cross the Connecticut-New York border going over the Byram River. The arterial pressure category of 120 milligrams of mercury is an interval that is defined by two borders, or two real limits, a lower limit of 119.5 and an upper limit of 120.5. 119.7, 120.2, and 119.5 all fall within the real limits of 120 milligrams of mercury, but 119.4 or 120.7 don't. Data collection requires that we make measurements. Measurement involves assigning individuals or events to categories. The categories can simply be names, such as male, female, or employed, unemployed, or they can be numerical values, such as 68 inches or 175 pounds. The complete set of categories makes up a scale of measurement, and the relationships between the categories determine different types of scales. The distinctions among the scales are important because they identify the limitations of certain types of measurements, and because certain statistical procedures are appropriate for data collected in some scales, but not in others. The word nominal means having to do with names. Measurement on a nominal scale involves classifying individuals into categories that have different names but are not related to each other in any systematic way. For example, cell phone or social security numbers. They don't represent quantities of anything. They're just numerical names. Other examples of nominal variables include nationality or eye color. The measurements from a nominal scale allow us to determine whether two individuals are different, but they do not identify either the direction or the size of the differences. Rooms or offices in a building may be identified by numbers. Room 109 is just a name and doesn't reflect quantitative information. Room 109 is not necessarily bigger than room 100. It's certainly not 9 points bigger. Averaging nominal data is either impossible or meaningless. Adding up the shirt numbers of the 5 hockey players currently on the ice and calculating their average, it doesn't represent anything meaningful. Similarly, you can't calculate an average by adding apple plus peach plus orange plus lemon plus peach plus apple and then dividing by 7. The categories that make up an ordinal scale not only have different names, but also are organised in a fixed order corresponding to differences of magnitude. Often an ordinal scale consists of a series of ranks, first, second, third, and so on, like the order of finishing a race. Sometimes the categories are identified by verbal labels, like small, medium, or large. The fact that the categories form an ordered sequence means there's a directional relationship between categories. With measurements from an ordinal scale, you can determine whether two individuals are different, and you can determine the direction of difference. So for example, person A is taller than person B. However, ordinal measurements do not allow you to determine the magnitude of difference between the two individuals. So you can't tell by how much taller is person A than person B. An interval scale consists of ordered categories that are all intervals of exactly the same size. Equal differences between numbers on the scale reflect equal differences in magnitude. However, the 0 point on an interval scale is arbitrary and does not indicate a zero amount of the variable being measured. For example, you know that a measurement of 80 degrees Fahrenheit is higher than 60 degrees Fahrenheit, and you know it's exactly 20 degrees higher. But a temperature of 0 degrees Fahrenheit does not mean that there's no temperature, and it does not prohibit the temperature from going even lower. The value 0 is assigned to a particular location on the scale simply as a matter of convenience or reference. Because of this, the ratio between 2 points on an interval scale are meaningless. A ratio scale is an interval scale with the additional feature of an absolute 0 point. With a ratio scale, ratios of numbers do reflect ratios of magnitude. A ratio scale is anchored by a 0 point that is not arbitrary, but rather is a meaningful value representing none, or a complete absence of the variable being measured. For example, an individual who required 10 seconds to solve a problem, so 10 more than 0, has taken twice as much time as an individual who finished in only 5 seconds, or 5 more than 0. With a ratio scale, we can measure the direction and size of the differences between two measurements, and we can describe the difference in terms of a ratio. For biostatistics, scales of measurement are important because they influence the kind of statistics that can and cannot be used. Let's go through some examples and practice identifying scales of measurement. What scale of measurement is used here? Nominal, ordinal, interval, or ratio? And are the variables discrete or continuous? Marital status is a nominal category, and it's discrete. The sizes of McDonald's drinks and fries are ordinal and discrete. Weight is ratio and continuous. The number of dreams recalled is ratio and discrete. Golf scores are interval and discrete. The time it takes for a light bulb to burn out is ratio and continuous.